here, if only to be recorded. Yeah, so what I've brought with me is not a recent paper or something I want to talk about, but it's rather by now semi-classical conjecture in bounded cohomology that I've been obsessed with for the last, I don't know, 15 years. And what I want to talk about is, well, the general framework of the conjecture. First of all, I want to give you the statement of the conjecture, which is fairly easy to state, although the statement itself is maybe not that enlightening. And a large part of the talk, I would like to discuss a little bit what is actually the meaning of the conjecture and why, as a geometer, one would care about it. And well, the conjecture is about a certain isomorphism, and it naturally breaks into several parts. There's a surjectivity and an injectivity part, and also different methods in rank 1 and higher rank. And I will survey a little bit what different people have done in order to study this conjecture and give a bit of an impression of all the different methods that have been inspired by this conjecture. Okay, so let's start by stating the conjecture in its most brutal and maybe uninviting form. We'll later give a more inviting version of it. So in its, most broadly, this isomorphism conjecture, well, it's a conjecture from the field of topology of Lie groups and symmetric spaces. And what's rather specific about it, that it's also about some, well, infinite objects, namely boundaries of Lie groups and symmetric spaces. So if you're not an expert in the field, the way you might read it is roughly as follows. So the conjecture states that there is a natural transformation between two variants of group cohomology for Lie groups, and for certain nice Lie groups, this natural transformation is an isomorphism. Okay, so the one word we can all agree on is isomorphism, and that's where the conjecture has a name from. So two things are isomorphic. So what they are, well, two versions of cohomology. And I will explain these two versions in a minute. And once I define these two versions of cohomology, you will see that there is a natural map between them, and we will see whether it's an isomorphism or not. And the conjecture applies to certain nice Lie groups, and it's perfectly okay. I mean, if you are not an expert on Lie groups, I mean, if you think of SLN-R or SLN-C or maybe a symplectic group, that's general enough to understand all the ideas that are presented here. So not much about Lie groups, needs to be understood. But what I need to explain to you is what are these cohomologies that are involved in this conjecture, and why do we care about them? And so I should give you one warning right away that, you know, almost any topological conjecture can be stated like this. I mean, if you state Farrell-Jones conjecture or something, you also just say, okay, there are two cohomology things and there's a map between them and it's an isomorphism. So that's not really saying much. So the question is, what is the meat of the conjecture? And the meat of the conjecture is that, well, some type of equivariant cohomology of a Riemannian symmetric space, or some generalization of hyperbolic space, is faithfully reflected by some measurable object called the Fürstenberg boundary of that space. So the conjecture is interesting for geometers because it connects two different types of mathematics. On the one hand, like Riemannian geometry, or rather a homological shadow of that. And on the other hand, outcomes of random walks or, well, boundaries. Yeah, these kind of objects. But okay, this is kind of the semantics of the conjecture. As far as the syntax is concerned, the formulation, it's all very dry topology, and it's just stated in terms of various variants of group cohomology. So let's first review what we need from group cohomology. So, okay, my notation for group cohomology is like this. So I'm only looking at group cohomology with trivial real coefficients. That's just, for laziness mostly. Gamma will be my group, and I look at its cohomology. So I don't know about this audience so specifically, so I guess different people have different ways to view group cohomology. I guess since this is a topology seminar, I should start with a topological definition of cohomology. So for most topologists, I guess group cohomology is just a cohomology of the classifying space. And if you have this point of view, that's perfectly fine for this talk. If you are more algebraically inclined, you might think of cohomology as a derived functor, say of the functor of gamma invariant in the category of R gamma modules. And this point of view is very abstract, but it has, of course, the advantage that you can use it to give various different models for group cohomology, which may be more concrete or more suitable for computations. And one concrete combinatorial model that I'm going to use a lot in this talk is a so-called bar resolution of cohomology. So what are my code chains? Code chains are just maps from gamma to some power, to say the real numbers, which are invariant under gamma, and my differentials are just the usual differentials where I always leave out one variable at a time in my code chain, and well, sum this with alternating things. So that's the usual differential. And if I take this complex and its cohomology, that's group cohomology. And I hope that everybody can agree on this, whereas other models might be more up to taste. And so to define the cohomologies that I will talk about today, I could either generalize the topological, the algebraic, or the combinatorial framework. And I will start with the combinatorial one because it's the easiest to modify. It's not the most useful one to modify because the meaning isn't so clear immediately, but it will give me a quick way to define the objects we are going to talk about. So how can you modify the definition of group cohomology? Well, in the definition of group cohomology, your code chains are just given by maps from gamma to the n into the real numbers. And if you want, you can add some adjectives to this map. For example, if you have a topological group, you could only look at continuous maps into the real numbers. Or maybe just Borel measurable groups that will be important for me. It's maybe not something topologists think about so much. Or if you have locally compact groups or Lie groups, you might think of Haar integrable maps. And one very basic thing you can, of course, do if you're talking about the real numbers, you can look at maps which are bounded, meaning that they have a bounded image. Okay, and so instead of looking at this complex of maps, you can look at the complex of maps where you only look at boundless maps, or only at continuous maps, or only at Borel maps, or only at continuous bounded Borel maps, whatever you like. And well, in each case, you can take the cohomology of this complex, and then you get some flavored group cohomology with an extra flavor. For example, continuous group cohomology, Borel cohomology, L1 cohomology, bounded cohomology, whatever you want to do. And you can do that, but there's no guarantee that that the outcome gives you anything reasonable. So that's a bit of the problem with this definition. And one thing I will need in a minute is it's also not so important that you have the group itself here. I mean, you can replace it by some G space X. I mean, maybe you want to twist the whole construction by a more complicated space and the group acting on itself. And then you get something that I would call action cohomology. You look at maps from X to the real numbers, which are G invariant, and X square and so on, and the same differential works. And if you want, you can add all the adjectives that you want before. Okay, this is just a quick way to define a lot of functors on groups and spaces. And as I said, the problem is that most of these will be completely meaningless, but there are two of them that turn out to have a meaning, which I will try to explain in this talk. So now I can state the isomorphism conjecture in its rough form. So as I said, this is a conjecture about Lie groups. And if you don't know much about Lie groups, as I said, think of SLNR or SLNC or SP2NRC or maybe SON1 if you want. And so the Lie groups I want to consider should have some properties which are listed here. Should we say connected semi-simple, finite center, no compact factors. I will just call it nice, and all these examples, they will be nice. And if you have questions about specific hypotheses, I'm happy to answer them. But for now, it's just a nice matrix group. That's how you should think of it. And we are going to look at two types of cohomologies. One is a continuous bounded cohomology. So code chains are just continuous bounded function on my Lie groups, or well, several variables into the real numbers, and well, they should be then cocycles. And the other cohomology I'm going to look at is so-called continuous cohomology, where I just require the code chains to be continuous, but not necessarily bounded. And of course, whenever I have a continuous bounded code chain, it's also a continuous code chain. I can just forget about the boundedness, and this gives me a natural transformation. Sorry, I have some technical issue. This gives me a natural transformation from this continuous bounded cohomology to the continuous cohomology, which is called the comparison map in the theory. And the conjecture simply says that this map is an isomorphism for all nice Lie groups and in every degree. So basically, whether I put this boundedness requirement in or not gives me the same cohomology groups. Now, this conjecture has a long history. I mean, the subjectivity part was formulated in a different language as far back as 1978 by Dupont. This version was made famous by Nicolas Monod, who stated this at his ICM address in 2006 in Madrid as, for him, the most important problem in bounded cohomology. Okay, so this is a conjecture. So I have two cohomologies, continuous and continuous bounded. There's a natural transformation, and the conjecture claims it's an isomorphism. Okay, so okay, I will remind you of the precise definitions of these cohomology series, but I mean, there's a more basic problem we should address, namely, it's not at all clear what it even means. Yeah, I mean, we have two vector spaces and they are isomorphic. Okay, I mean, what does it mean? Why do we care? And then also, how do we approach this? So these are the three problems I want to address. I think the first half of this talk will only be about like what it even means. And then in the second half of the talk, I will give you some approaches how to settle this conjecture and tell you what is known about the conjecture so far in the last 20 years. Okay, so yeah, as I said, before I get into more details about what one can do and what is known, let me clarify the meaning of the objects in the conjecture. So the first object that we have seen here is continuous cohomology. So I remind you, it's just defined like usual group cohomology, except that the cochains are required to be continuous. Now, I will only consider this for locally compact second countable groups. Think of Lie groups, think of matrix groups. That's a framework I will work with. And in this case, it doesn't really matter whether I work with continuous cochains or Borel cochains. I mean, however you do it, if you, in the case of Lie groups, you can also take smooth, I mean, locally smooth cochains, it's all the same. That does not matter. But what does matter is that this definition is not the same as what people in topological groups are maybe more used to studying, namely the cohomology of the classifying space of a topological group. That's something very different. And there is a natural transformation from this into continuous cohomology, but continuous cohomology is not easily identified as cohomology of a space. Yeah, it's something associated with a topological group. It comes from a simplicial space, namely from the simplicial space of EG, but not from its geometric realization, because for non-discrete simplicial spaces, the cohomology is different from the cohomology of the realization. Yeah, that would be the cohomology of the realization, but that's not what we're doing. And so how one should really think about this is it's a certain derived functor of the G invariance in a certain category of modules, and the category happens to be, duals of separable continuous Frechet modules over the group. So it's some technical category that you work with. And this means that there are many different models that you can give. And one model that you can give is you take just any proper G space, for example, the group itself, and then you just look at continuous functions for the G action in the space. And in general, it's a bit hard to say what this computes, but we will be interested in nice groups. And this will be groups which act on some nice properly, meaning with compact stabilizer, on some contractible smooth manifold, X. And in this case, there's a very nice model for this continuous cohomology. You simply look at differential forms on this manifold on which your group acts, and then you look at G invariant differential forms, and you take the cohomology of that complex. And this is a continuous cohomology. And so it's sometimes called equivariant de Rham cohomology. It's related to equivariant cohomology, but depending on how regular your group is, there might be some differences. So that's my notation, for the space.
Can I clarify? So these are finite dimensional vector spaces?
Right. So in this case, these are going to be finite dimensional vector spaces.
Okay,
Whereas
but in
for a
general, you
general
might have
group,
a
it could be
Frechet
infinite.
space.
Yes, in this case, they happen to be finite dimensional, and also there are only finitely many of them because the manifold is finite dimensional. In general, there might be infinitely many of them, and it might be infinite dimensional Frechet spaces. So
Thanks.
if your group has a nice action on a manifold, they become finite dimensional and just nice vector spaces. So we don't have to be afraid of them. And so in the conjecture, we only care about this for nice Lie groups. And nice Lie groups are isometry groups of nice metric spaces, namely Riemannian symmetric spaces of non-compact type. So think of SL2R acting on the hyperbolic plane. Yeah, the hyperbolic plane is a very nice, smooth two-dimensional manifold, and you act there with a compact stabilizer. So the symmetric space is actually the Lie group modulo some compact stabilizer. It's even a transitive action on the manifold. And so the continuous cohomology of the Lie group, of this nice Lie group, will just be the equivariant cohomology of that manifold. So that's some finite dimensional object that you get by looking at, well, in the case of SL2R, just invariant differential forms on the symmetric space. So in that case, on the hyperbolic plane. And well, I mean, there's a completely algebraic way to compute this because, okay, what's a differential form on the symmetric space? So if you have a Q form on G mod K, which is G invariant, then it's just the same as something in the exterior power of the normal bundle at the point. Yeah. And so well, if you have your Lie algebra here, so that's the tangent space of the group at a point, then you have the tangent space of the stabilizer, and you have here the normal space, then this cohomology is a completely algebraic object which depends just on this Lie algebra and, well, the subalgebra corresponding to the stabilizer. In fact, what you can do is you can actually replace the normal space by, well, I times the normal space and turn this Lie algebra into a different Lie algebra. And this would be a Lie algebra of a compact group. That's a standard technique in Lie groups. And this allows you to turn your non-compact group G, something like SL2R, into a compact group G hat. So there is a certain duality between Lie groups, which allows you to turn non-compact group into compact groups. And then dual to this symmetric space, for example, the hyperbolic plane, there's a compact dual symmetric space where you just, well, change kind of the direction of the normal direction. You rotate the normal space by 90 degrees in a sense.
So what is G hat in the case of SL2R?
So in the case of SL2R, the complexification would be SL2C, and G hat would be SU2, the maximal compact of the complexification. And so in this case, this space would just be the two sphere. Okay, so the dual of hyperbolic n sphere is the dual of hyperbolic n space is the n sphere. Hyperbolic n space has constant negative curvature, and the n sphere has constant positive curvature. So you just put this extra I to change the sign of the curvature. And so with every symmetric space, you have a dual one where the curvature is just changes signs. And what you get from this formalism is that this continuous cohomology of the Lie group is just the usual singular cohomology of that compact dual symmetric space. So in the case of the hyperbolic plane, it would just be the singular cohomology of the sphere. So the continuous cohomology of SL2R is just generated, well, it's one dimensional in degrees 0 and 2, and everything else is 0.
In complex hyperbolic, this is complex projective, and then quaternionic hyperbolic,
exactly.
Quaternionic projective. Like these are, it's like the compact dual.
Yeah, it's just a compact dual. I mean,
yeah, okay.
The complex or quaternionic hyperbolic would dualize to the complex or hyperbolic projective space.
Right. And then it's just the typical relationship you get, you know, like even lattices in those non-compact Lie groups, they get cohomology from this compact dual.
Exactly.
Like this is like, these are like the canonical classes, or, you know, the kinds of things that you sort of expect of all the lattices.
Exactly. That's what's called Hirzebruch duality. That's exactly what's going on.
Okay, thanks.
Yeah. And so, but if you want to think of the generators concretely, I mean, for example, SL2R has a generator in degree 2. Well, you have an invariant 2 form on the hyperbolic plane, namely the volume form. How do I produce a cocycle? So a cocycle would be a map in 3 variables on the hyperbolic plane, which is SL2 invariant. So how do I get such a map? So my cocycle should take 3 points in the hyperbolic plane and produce a number. How do I do this? Well, 3 points in the hyperbolic plane, they give me a geodesic triangle, and I just integrate the invariant form over this triangle, and this gives me a cocycle, right? And this is the way how I can identify invariant differential forms on the hyperbolic space that I'm in with continuous cohomology of the Lie group. Okay, so the cocycles in this cohomology are just integrals over differential forms on this generalization of hyperbolic space. So that's what continuous cohomology is. And Borel in his PhD has computed in all cases, not just for hyperbolic space, but also in higher rank, what these cohomologies are. So it's completely explicit. Yeah, it's just the cohomology of these compact dual spaces, or if you want, it's given by integrating these differential forms on the symmetric space. Okay. So that's continuous cohomology of nice Lie groups. It's just differential forms on generalizations of hyperbolic space. So that's the right-hand side of the conjecture. What about the other side? What about the continuous bounded cohomology? That's less classical. One important thing is that also it doesn't really care. It's called continuous bounded cohomology, but it's the same as bounded Borel cohomology. So continuity doesn't really play a role here. It's also derived function, this time in the category of duals of separable Banach modules. And the important thing, which is due to Burger and Monod, is that it can be actually computed in a very nice way. Namely, to compute this continuous bounded cohomology, you can use bounded measurable cochains, but not necessarily on G, but on any space B. And B stands for boundary. So the technical condition is an amenable G space. And the space you could think of here in general would be something like the Fürstenberg boundary, so the outcome of random walks on such a thing. So it's a probabilistic object. It doesn't have a topology, but it has a measure structure. And so you can do this measurable cohomology of that, and this will give you bounded cohomology. So continuous bounded cohomology is something which comes from random walks on that group. However, for nice groups, there's actually a very nice topological model that I'm going to explain. So first of all, there's a reduction to a nice case, which is implicit in the conjecture. Namely, if you have any connected locally compact group, then it always has a quotient, which is a nice Lie group. So you can always mod out a small subgroup and get a nice Lie group. And this subgroup happens to be amenable. So every random walk there has a trivial outcome. And this means that the continuous bounded cohomology of that Lie group, or locally compact connected group, will be the same as the one of this quotient, because continuous bounded cohomology doesn't see an amenable subgroup, so you can just mod out this guy. And so if you want to know the continuous bounded cohomology of all connected locally compact groups, it's enough to know it for these nice Lie groups. You have an immediate reduction to this case. And that's why the conjecture only talks about these groups. All the other ones are reduced to those. And if you have these nice Lie groups, well, they are basically symmetry groups of symmetric spaces, like think of SL2R acting on the hyperbolic space. And now the question is, what is the boundary that you can use to compute the bounded cohomology? And the boundary happens to be just the so-called Fürstenberg boundary of the symmetric space. In the case of hyperbolic space, this is really just the boundary of hyperbolic space that you think about. I mean, the usual boundary, the sphere, at infinity of the hyperbolic space. So what this says is the bounded cohomology of your Lie group is just given by measurable cochains on the boundary of the symmetric space. In higher ranks, there are many boundaries, so the correct one is the Fürstenberg boundary, but the difference will not be so important for this talk. And could also take the geometric boundary. Okay. So here's how you should think about this again. Let's think again in the case of SL2R. So in the case of SL2R, again, this one knows that the second bounded cohomology is one-dimensional. And what's the generator? The generator is, well, is given by a cocycle, and this cocycle is now a map from triples of point on the boundary of the hyperbolic plane to the real numbers. Yeah, now I need a bounded measurable map on the boundary of the hyperbolic space. So what can I do if I have 3 points on the boundary of hyperbolic space? Well, if I have 3 points on the boundary of hyperbolic space, I can still draw a triangle. It's now an ideal triangle. I mean, the endpoints are at infinity. But because I'm negatively curved, this ideal triangle still has a finite volume. So I can still define a cocycle by integrating my volume form over this ideal triangle. This gives me a cocycle on triples of points on the boundary of hyperbolic space. And well, if you think about it, I mean, there are not so many volumes that a triangle, an ideal triangle in hyperbolic plane can take. So this is either pi or minus pi, depending on the orientation. So up to a constant, you just get the orientation of 3 points on the circle. So something is different here, namely, first of all, the cocycle is no longer continuous. Yeah, you have to forget it, even though it's called continuous bounded cohomology, you have to forget about continuity. This cocycle will jump if 2 points collide, but it's still measurable and it's bounded. It actually only takes finitely many values. Okay. So, yeah, and what we see now that the generator we get in continuous bounded cohomology is in a very obvious way an extension of the generator in continuous cohomology. Before we had this cocycle coming from integrating inside our space, and now we are integrating all the way to the boundary of the space. Yeah. And what is the statement here? The statement here in this example is that the continuous cocycle on the symmetric space extends to a bounded measurable cocycle on the boundary. And the reason that you can extend this is basically negative curvature, which tells you that these integrals remain finite. That's precisely negative curvature. Yeah, if you do this in Euclidean space, all your triangles will have infinite volume, and this will not be. Okay, and well, the problem is that in general, our symmetric spaces only have non-positive curvature. There will be Ket0 spaces. And so it's not so clear how you can extend cocycles given by integration of a differential form on the space to the boundary. That's not clear at all. Still, what does the isomorphism conjecture say? First of all, it claims that whenever you have a continuous cohomology class, so that's basically a differential form on the symmetric space, there's some measurable bounded way to extend it to some cocycle on the boundary. So all these cocycles in the space can be extended to the boundary. And that's what's called the surjectivity part of the conjecture. And that's a very old conjecture of Dupont from the 70s. And the more adventurous part of the conjecture is that, in fact, there are no other bounded measurable classes on the boundary. They all come from extending something from the inside. And this part of the conjecture is fairly new, and it's not so clear how much support there is for this part, because until this year, people also thought, maybe I can just take, just measurable cocycles on the boundary and not, remove this boundedness requirements. Maybe it always gives you the same. And only this year, last year, there was work by Monod and Michel Boucher and Savigny, who gave the first example. They computed what happens if you remove the boundedness condition and you get additional cocycles on the boundary. So it's not true that you can extend every cocycle to the boundary and that gives you all the measurable cocycles on the boundary. The boundedness is somehow essential for this to work. And so this is now the actual content of the isomorphism conjecture. It tells you all these cocycles given by integrals in the symmetric space can be extended to the boundary, and this gives you all the cohomological information that this boundary has. Yeah, that's conjecture. And yeah, for SL2R, we have already seen surjectivity works, because there is only one class, there's only the volume class, and this one does extend. And you might think that injectivity, well, I don't see any other cocycles on the boundary. How can I define an invariant number to 42 points on the boundary? Well, as a matter of fact, it's still open. Nobody has any idea what the 24th continuous bounded cohomology of SL2 is. Yeah, and that's very different from continuous cohomology, where due to differential forms, it has to stop after the dimension of the symmetric space. In continuous bounded cohomology, it's completely open. We have no idea what happens beyond even in high dimensions. Okay, that's all I wanted to say about the motivation of this conjecture. So what you should keep in mind is continuous cohomology is what least theorists study when they want to study the geometry of a symmetric space. Bounded cohomology is the information you get from the boundary at infinity as outcomes of random walks or whatever you want to think of it. And the claim is that cohomology doesn't make a difference whether you work in the geometric setting or in the boundary setting. So the boundary fully reflects everything about the cohomology and doesn't have any extra information. And that's a conjecture. And if you care about, cat zero geometry or asymptotic geometry of groups, this is something you might want to consider. Okay, so that was the conjecture.
Question, Tobias. I got confused about the last question. So this volume form is a degree 2 continuous bounded class.
Yes.
On SL2, and presumably its powers are also continuous bounded. Is it not?
Yes,
true?
but they happen to be co-boundaries. For example, if you, right, if you take its cup product with itself, in usual cohomology, you know that the 4 form is 0. If you do it on the boundary, you do get a form, and it has a primitive. And if you go into cross-ratio coordinate, this is the Rogers dilogarithm. So the theory of polylogarithms is basically related to what you get when you take powers of volume forms and look at what their primitives are. So for the powers of the cup product, we know that they are of the volume form in bounded cohomology, we know that they are trivial. But
okay.
Yeah, but it's not clear at all. It requires the theory of the dilogarithm to prove that. It's basically the functional equation of the dilogarithm. So for differential forms, we know if they get too many variables, they die. But for functions on the boundary, there's no reasons why there shouldn't be very crazy co-cycles in 42 variables on the boundary. No.
Thank you.
So that's the conjecture. Now, I want to tell you a little bit about the results that we have concerning the conjecture, and some, in particular, those results which motivated the conjecture, and also some more recent results. So I will start with the surjectivity because, the surjectivity is, we understand a bit better. So surjectivity, I remind you, is the question whether we can extend all the differential forms to the boundary in a homological way. Okay, so here's a very basic fact. So let's first look at the case where we are of rank 1, meaning our space is really negatively curved. Negative curvature, meaning it's a real complex or quaternion hyperbolic space. And you know that if you are in a hyperbolic space, then ideal simplices have finite volume. Yeah. You can do geodesic simplices at infinity, and they always have finite volume. And this gives you a way to extend the volume class to the boundary. So you can, so this means in our language, it's a comparison map in top degree from the continuous bounded cohomology to the continuous cohomology is surjective, because here there's only the volume form, and the volume form can be extended to the boundary just by integrating along ideal simplices. And this is the theorem of Gromov and Thurston, which is known as positivity of the simplicial volume in negative curvature. So it hasn't anything to do with Lie groups. It's just a fact about negatively curved groups that you can extend things. But if you do this in the Euclidean space, of course, you cannot do this. And so the question was what happens in higher rank? So if you have, say, SL5R, you have 4-dimensional, you have R4 embedded into that symmetric space. And if you take a triangle which happens to live dumbly in this R4, then, well, if you make it bigger and bigger, the volume will go to infinity. So you cannot extend for all triangles this volume form to the boundary. This doesn't make sense. But you might say it's very rare that 5 generic points will not lie in a flat, and so it shouldn't really happen so often.
Sorry, what is the Furstenberg boundary of a flat?
The Furstenberg boundary of a flat will just be a circle.
Okay.
It will be the circle at infinity. Yeah.
Okay.
And yeah, so no, that's not true. It will actually be a finite set. Sorry, it will be the Wald chambers in that flat. So the set of asymptotic Wald chambers in that flat. So depending on your type, it will be a finite set.
So for a Euclidean plane, is it a point?
If you just take a Euclidean, well, this Fürstenberg boundary is really only defined. Yeah, okay. If you want to define it this way, I mean, he only defined this for symmetric spaces, but it would be a point.
Right. Yeah.
Okay. So the question is, if you have only non-positive curvature and not negative curvature, can you still extend this to the boundary almost everywhere? And this is actually true. So this was conjectured by Dupont and proved by Lafont and Schmidt, except for the case of SL3R, which was later filled in by Michel Bichet. And so they extended this. But I mean, what you have to do, it's actually delicate in the terms of analysis. You have to bound the Jacobians that appear in this, of the volume form. And they managed to do this, and therefore they proved that, yes, in top dimension, the comparison map is surjective. So that's positive of simplicial volume of locally symmetric spaces. And I say the best result I know in this direction is of Lafont and Wang in 2018. So it's still an active area of research, which concerns a case of small codimension. So if you have a really high dimensional symmetric space of large rank, then if your degree is very close to top, you're still surjective. Yeah. And this uses tools from analysis and differential geometry, namely bound on P Jacobians. So that's fairly technical, and it gives you the best known results in big degrees, but it has very little chance of getting you to smaller degrees. So if you want to know about smaller degrees, this doesn't work. And so this idea that you control integrals.
Yeah, I would say on that front, I think how low you could go should be a function of the real rank of the Lie group. Like within, like when you're going from the dimension, the symmetric space, maybe down to the, codimension real rank, like these kinds of methods would be good for that. But like once you get below the real rank in terms of, bigger than the real rank in terms of codimension, then there's no hope that you could use these kinds of methods.
Right, and they are fairly close to that. They have here this +2 that they want to get rid of, I think. But I don't think yet.
Right.
For SL,
it just gets technical with these P Jacobian estimates, because that's part of stuff I've worked on, and it really is hard. I mean, it's really awful optimal optimization problem. I mean, they're just really awful calculus problems that are not like humanly doable, to be honest. So, but yeah, I don't want to interrupt. Sorry.
So yeah, this Lafont one is a very nice technical paper, I think, on this. But so there are other methods which are purely combinatorial, and they are based on primary characteristic classes. So the idea here is, if you have a Lie group, you can also look at it as a discrete group. It's a discrete topology. And so the inclusion, I mean, you have a continuous map from G with a discrete topology into G. And this gives you a map from the cohomology of the classifying space of BG into the cohomology of the classifying space of the discrete group, which is just the group cohomology of the discrete group. And the image of this map is, well, these are universal characteristic classes of flat G bundles. Yeah, discrete topology means you're looking at flat G principal. So classes in this image are called primary characteristic classes of flat bundles. And for these, you have certain combinatorial representatives using models for classifying spaces. And in fact, you can always find a representative for a primary characteristic class which takes only finitely many values. So this is an old result of Gromov. I mean, the proof you want to read is the thesis of Michel Bichet, and she proved that, due to, well, these are semi-algebraic sets, and by some algebraic or semi-algebraic geometry, you get that they can only take finitely many values. So those classes in the cohomology of the discrete group coming from the cohomology of BG, they are always bounded. Actually, they only take finitely many values. And this can be exploited. So in joint work with Andreas Ott, we looked at the following. So I told you that the cohomology, the continuous cohomology of a Lie group is not the same as the cohomology of the classifying space. But there is a natural transformation from the classifying space to the continuous cohomology. In the case of Lie groups, it's given by the characteristic classes of the universal bundle over the compact dual symmetric space. But it doesn't matter. There is this map. And if you go down to the discrete group, I mean, it's a natural transformation. You see that you have here the image of this map here that you get. So maybe the image of this map is the primary characteristic classes, and they are bounded. So they come from the bounded cohomology of the discrete group. And now the point is that there is a way, if you have a cohomology class, a bounded cohomology class or normal cohomology class of the group with a discrete topology, you can extend it back up to the continuous group. And this is done by integrating over a lattice. These groups have lattices, and by a transfer argument over a co-compact lattice, you can retract the cohomology of the discrete group to the topology of the continuous group. So this is a way to so the continuous cohomology embeds into the cohomology of the discrete group, and it's even a retract. And the same retraction also works for bounded cohomology. And this implies that those classes which are primary characteristic classes, well, they lie in the image of the bounded cohomology, and therefore, if you happen to be up here in the image of this natural transformation, then down here you are a primary characteristic class, therefore you come from the bounded cohomology, and then using the retraction you can go back up, and therefore you are bounded. So basically, using Gromov's boundedness of primary characteristic classes and a bit of a diagram chase, you prove that the image of this natural transformation from the cohomology of BG to the continuous cohomology consists of bounded classes, even taking finitely many values on the fundamental domain. And now the question is, what is this natural transformation? It's given by some naturality, but you can actually compute it using what was mentioned before by Ben. This is Hirzebruch duality. Like there's a relation between cohomology of lattices in Lie group and the cohomology of the compact dual symmetric space.
Tobias, may I ask a question?
Yeah.
Just two questions. So just to make sure, the bottom right map, when you wrote surjection, so you mean surjection to the image of
to the image of the
it's not surjection to the entire.
No, sorry. It's just it's onto the image of the map coming from the left. Yeah.
Right. And then you said that the right vertical map is injection for what Lie groups?
For this is for all Lie groups. I mean, or for all the semi-simple Lie groups. I mean, for all Lie groups which have a co-compact lattice, because then you can integrate back.
I see.
You can go further down from the discrete group to a lattice, and then go up from the lattice by integration.
Right. Thank you.
So using
I guess this holds then for like reductive groups. Like don't reductive groups also have co-compact lattices always?
Not always. I mean, for most, yes. It depends on what you mean by reductive.
Well, I forget. Yeah, well, yeah. I thought there was a result of Borel and Harda that they proved under some conditions that like a reductive Lie group had a co-compact lattice. They don't always have non-co-compact lattices. I thought was one of the. Oh, is it? It's
no,
maybe that was the thing. Yeah, you can.
Here, that's fine.
Well, I know you need co-compact here for that, because you don't want just finite volume. Because you wouldn't get the bounded from that. You need the compactness for the.
No, you need to you need co-compact for the other one. For the bounded, I mean, finite volume would be fine, but.
Okay.
Continuous function, you can only integrate over compacting. A bounded function with finite measure would be enough.
Yeah, but there's a fair class of Lie groups that admit co-compact lattices.
Right. I mean, all the ones we care about for the conjecture that we have reduced to, they have lattices.
Yeah. Of course they do. Yes.
and the continuous cohomology actually splits. There is an even part and an odd part. So the even part is that's not quite correct. It's a truncated polynomial algebra on even generators, and then there is an odd part which is an exterior algebra. And what we compute with Andreas Ott is that the even part is precisely the image of this natural transformation. So the cohomology ring of a Lie group of continuous cohomology is finitely generated by finitely many generators that are explicit by Borel. and they're even and odd generators, and all the even generators are bounded. And so they take finitely many values. You can see already the difference for SL2R in the hyperbolic plane. It's even the generator, it's degree 2. So the volume of a triangle takes only finitely many values. For SL2C, which is dimension degree 3, which is odd, it takes infinitely many values. So the even ones are special and they are bounded. And for about 2/3 of, I mean, there's a list of all simple Lie groups. And for about 2/3 of them, they are only even generators. So we have proved the surjectivity of the conjecture for groups like SL2R, SUPQ, SP2NR, all the groups which have a complex structure on the symmetric space, and also many others. There are some bad guys, which are SLNC, SO33, and a few others. So like about 1/3 of the guys we cannot get because they have odd generators. For example, SLNC is really bad. It has only odd generators. So this is not so good. So what's my conclusion for the surjectivity? So the surjectivity part is solved for many Lie groups of interest, roughly 2/3 of them. And just by these combinatorial methods using characteristic classes and Hirzebruch duality. The analytic methods, they work in high degree, but you cannot push them down too much further. And so what is missing are these odd generators, and they are given by so-called secondary characteristic classes. And Dupont conjectured almost 50 years ago, well, 40 years ago, 45 years ago, that they are bounded, and there has been basically zero progress on that so far. So we are stuck a little bit in the surjectivity, but in general, we are in good shape because for many groups we know it, and for those where we don't know, there's a reason that we don't know it because there's this hard conjecture that's still open, and yeah, not much progress has been made. Okay, so that's what I wanted to say about the surjectivity. So, okay, if you are willing to restrict to half of your Lie groups, you can prove it. That's the status. And funnily enough, these soft methods from homological algebra and duality, they seem to do better than this really hard analytic methods in low degrees. In high degrees, the analytic methods are unbeatable, I think. Okay. So that was the surjectivity. And I spend now like a lot of my time on surjectivity, and that's because injectivity not very much is known. Yeah, so that was already most of the good news I have on the conjecture. So let's first look at injectivity for rank 1 Lie groups. Rank 1 means we are looking at hyperbolic spaces. So we have a Lie group which acts on a space of negative curvature. And so what do we know about injectivity of the comparison? So if we are in degrees at most 2, then the conjecture is true. Even in higher ranks, that's always true. And the reason is very specific to low degree. And it's a bit of a stupid reason. Because in degree 0, well, it's a derived functor of the invariance, so it's just always R. And the first bounded cohomology, you can think of it as bounded homomorphisms into R, and R doesn't have bounded subgroups, so that's always 0, so that's fine. In degree 2, it's kind of interesting. That would be a whole talk. But the kernel of the comparison map in degree 2 is given by so-called homogeneous quasimorphisms. So these are functions on my Lie group, which, well, are almost homomorphisms. So they satisfy f of g times h is almost f of g plus f of h. And they are conjugation invariant. And yeah, that's what they have to satisfy. And the problem is that Lie groups are boundedly generated by unipotents. So every element in the Lie group is just a product of 5 unipotents, say. And all these unipotents, they are conjugate to finitely many elements. And well, this means that this quasimorphism has to be bounded, and then because it's homogeneous, it has to be 0. So this is just something very specific to degree 2, which it's a structure theory of algebraic group, which tells you Lie groups are boundedly generated by unipotents, and therefore they cannot have quasimorphisms, and therefore there is nothing in degree 2. And okay, so that's a technique which is very powerful in degree 0, 1, and 2, and there's absolutely 0 chance of this to ever generalize to any higher degree. Yeah? So we understand these cases, but everything else doesn't tell us this. Now, there are only 2 results in degree bigger than 2 about injectivity. one is, or well, up to the last one that I'll mention later. In degree 3, we know that we are injective for SO2C and SO2R. And this is also a result by Burger and Monod, but this requires more work. And it uses something very special about these two groups, SO2R and SO2C, namely, these groups, they act essentially 3-tentatively on the boundary of the hyperbolic space. And this means that in degree 3, there are no co-boundaries. And this happens only for these two groups and only in degree 3, never ever else. And so to prove that you are injective just means that there exists no co-cycles in this degree, other than, okay, the volume form in SO2C. And so how you do this, you assume you have a co-cycle on the boundary, which is a sphere, and you look at the Fourier coefficients, and you get a contradiction from the equation that the Fourier coefficients must satisfy. So you show that there is no cohomology by showing that there are no co-cycles. And again, this method has no chance of ever generalizing because in every degree, at least 4, there exist co-cycles on the boundary, period. There exist G-invariant measurable bounded functions. And so what you have to do, I give you a bounded primitive, I give you an explicit co-cycle on the boundary, and you have to give me a bounded primitive for that co-cycle in that degree. And well, for this, there's a general method. So what you can, of course, do, you start with your co-cycle. The co-cycle is a function on the boundary in, say, I plus 1 variables, and it's G-invariant. And the important thing, it's bounded. It's a bounded measurable function. Now, you can always find a primitive for this co-cycle. You can just integrate over the boundary, or integrate over the maximal compact subgroup K if you want. And this will give you a primitive which is bounded, but it's only invariant under a compact subgroup K. Yeah, in the case of SL2, it will only be invariant under the circle, not under the full SL2. So you only produce a K-invariant primitive, but you need a G-invariant. So what you can then do is you can look at a certain space, you look at your one special primitive, and you add all possible K-invariant co-boundaries. So this is a space of all K-invariant primitives of a given cochain. So the space, I should say, of all K-invariant bounded primitives of your co-cycle C. And what we would like to find in this space is a G fixed point. Okay, so you have reduced the problem to a fixed point problem in a certain infinite dimensional space for your group of certain functions. And so how do you find a fixed point? Well, the group G is connected. So for a function to be constant, what you need is that all derivatives are 0. So this fixed point property, you can formulate it as a system of first order partial differential equations. So this is the approach which was found by Andreas Sotte and myself 8 years ago. One can formulate the problem of finding among all these K-invariant primitives and G-invariant primitives is the same as solving a system of first order PDEs. And so, okay, you can solve these PDEs explicitly by integration. And so what's the state of this? So this is work in progress. It's not done. But there's one good thing. This works for all rank 1 Lie groups in all degrees, and probably even in higher rank. And so what it does, the method, we produce explicit primitives for any bounded measurable G-invariant cocycle in high degrees. There's one small issue. We have to do an integration. We have to integrate a bounded function over an orbit. And the big problem is, how do we show that this integral gives us a bounded function? The integral converges. We can show this in all cases. The question is it a bounded function? And in degree 4 for SL2R, you have enough symmetries and it's always bounded. So that was the result in 2015. And well, Sam asked this question, what about cup products with volume forms? There we also have enough extra structure to prove that these are always bounded. But this requires some more ideas. So Andreas wrote a very nice paper in 2018 called Transgression in Bounded Cohomology, which is not very well known and which pushes this method kind of to its boundaries. And so we are now in the situation that we have gone to all people and have asked them to give us all the co-cycles you have on the boundary. And we have collected all the co-cycles people have thrown at us. And for all co-cycles everybody ever gave to us, we can prove that they have a bounded primitive. So all cohomology classes that you can write down are bounded. I mean, are trivial in high degrees. So the conjecture is true for all cohomology classes that everybody has ever given to us. But the problem is when you give me a function, it's already a nice function. Yeah. If you give me a function, it's given by a formula, it's already nice. And the problem is that the co-cycles we have are only measurable functions without any regularity. Assume any kind of regularity, the problem becomes trivial. Yeah. But so there might be hypothetical, very barely measurable functions where our integral doesn't yield a bounded primitive. So the problem is actually we have a lack of good examples to understand the mechanism. So we have a mechanism which in all easy examples works, and we don't really fully understand it. So I think there is an approach which has the potential to work for all rank 1 Lie groups in arbitrary degrees, but there is one analytic idea missing. And to find this, one probably needs some more examples of co-cycles on spheres. So that's a sad state of affairs. But yeah, for any concrete co-cycles, we can usually produce primitives, and this has a lot of applications if you do this for concrete co-cycles. Okay, so that is a disappointing news about rank 1. And in my last 2 minutes, let me briefly say what you do in higher rank. So there's a very neat result that I want to advertise by Carlos de la Cruz Mengual. He proved this here that if you have any complex, non-exceptional nice Lie group, then the comparison map in degree 3 is an isomorphism. And since I only have 2 minutes, I can only give you the 3 steps. So the proof is in 3 steps. The proof is by induction on the rank. So if you're in rank 1, the only rank 1 complex group is SL2C. And well, in SL2C, this works because degree 3 bounded cohomology of SL2C, well, is precisely where this integrals work. And the idea is to now let's take a group like SP200C, yeah, a symplectic group. I want to prove that the comparison map is injective by reducing to the case of SP2, which is just SL2, which is known. And the idea is that all the classical Lie groups come in families. So you have SP2, SP4, SP6, SP8. You have this whole family of Lie groups. And what we proved with Carlos is that if you look at bounded cohomology along such a family, then this bounded cohomology stabilizes as soon as, well, the rank of the Lie groups increases. So if you have Lie groups where the rank goes to infinity, then the bounded cohomology will become stable. And so if you want to know what is the third bounded cohomology...
Is that in every degree?
Yes, in every fixed degree. In every degree, no matter...
Okay, in every fixed degree, if you go far enough out, it stabilizes, what you said. Okay, right. Okay,
so
thanks.
For example, the third bounded cohomology of SP224 is the same as the third continuous bounded cohomology of SP48. Problem is the third bounded cohomology of SP48, we also have no idea what it is. Yeah. And then recently, Kastenholz and Sroka, they improved our range. So they bring it down to H3 of SP12 or something. But we still have no idea how this helps. And so Carlos had a really brilliant idea, which is to use what's called secondary stability to conclude. So we have these maps, iota n, between consecutive groups in our family, and they induce these maps in bounded cohomology. And we know that the kernels of this map are 0 if n is really, really big. And what we would like to prove to get down to SP2 is that they are not just 0 for large n, but for all n. And then what Carlos proved is that that actually these kernels, they can also be interpreted as some bounded cohomology for some action of symplectic groups. And they also stabilize, but they stabilize all the way down to SL2. And because we know by the primary stability that for large degrees, the kernels are trivial, you can use a bootstrapping argument and using the secondary stability, bring yourself down all the way to SL2 where you know everything. And this proves the stability. And so it proved that the third bounded cohomology of SB200 is the same as SB2, which is. And so this reduces then the main theorem to the rank 1 case. So in my last -1 minute, let me just summarize. So using techniques like Quillen stability for bounded cohomology that Carlos and I proved, one has a very good mechanism to prove cohomological stability. One needs good complexes to act the groups on, but you take the same as for usual cohomological stability. This still works. And this gives you some kind of stability in bounded cohomology. And using secondary stability, you can bring yourself down to a rank 1 situation where we have the other tools. And so this probably works quite generally in low degrees, but it requires rank 1 results. So we have the conjecture is proved, the surjectivity part is proved in many situations, like for half the Lie groups. The injectivity can probably be reduced, at least in low degrees, to the rank 1 case. But in the rank 1 case, as I said, we are this one idea short of how to get the boundedness. So I want to conclude by saying that there has been a lot of progress by very different techniques from all kinds of different areas of mathematics, but almost all progress was connected to new people looking at the conjecture with fresh eyes. And I think we're just missing one idea, and maybe one of the people in the audience can take a look at these papers and tell us what we are missing. I mean, particularly these papers of Andreas Ott and of Carlos de la Cruz, they're not yet well known. And I think these papers have really a lot of potential together to bring us really further with some new ideas to solving this conjecture. I'm sorry for going over time. So that's what is known about the conjecture so far. And it's still widely open, but still it's a nice interplay of a lot of different techniques from different areas of topology and geometry. And there's still a lot to be explored. And I'd be happy to explain more if any of you is interested in joining our obsession with this beautiful conjecture. Thank you very much.
Thanks for a great talk. Does anyone have any questions for our speaker?
Usually I think of secondary stability as comparing homology in different homological degrees. Is this a different sense, or is it just happens that there isn't a degree shift here?
There is some implicit degree shift here. You see, the kernel of these maps between bounded cohomology happens to be a bounded cohomology of the group acting on some projective space. And that's basically a shifting model. So there is some, in the paper of Carlos, he I think comments on this, the way he formulated in the paper, it's not so clear why this is a secondary stability result. But if you make this degree shift, which is implicitly explicit, I think it becomes a classical secondary stability result, I think.
And so at least one way of proving secondary stability is, you have a spectral sequence proving primary stability, and then you look at higher differentials. Is that at all related to what you do, or what happens here?
That's what I thought one should do, but we didn't manage because we didn't understand the high differentials. And Carlos managed to come up with another spectral sequence that we had discarded long ago, which is slightly different. In this primary stability, we use the same spectral sequence that Monod uses and also Sam uses in his work with Monod. For the secondary stability, he uses a different spectral sequence, but I feel one shouldn't. If one could understand better these higher differentials, one maybe shouldn't. But I must say, I don't understand the full details of these papers of Carlos. That's why I'm saying if an expert in homological stability looks at this paper, maybe there's something more to be extracted from it.
Thanks.
Maybe I have two questions about this lemma of Carlos.
Yes.
What is special about degree 3?
Yeah, that's a good question. probably nothing, except that degree 3 is the smallest non-trivial degree where something happens for the symplectic group. And so you have a lot of zeros below that in your spectral sequence. And you don't have to worry about interfering terms. I think that the general argument should go by induction on the degree. I mean, now if you have it in degree 3, you get a lot of vanishing of these induced maps in bounded cohomology in degree 3, and this produces you then something to go on in degree 4. However, in degree 4, you don't know the rank 1 result.
Oh.
So that's what I meant. Like you're somehow stuck from, yeah. I mean, that the PDEs don't work is a real problem that you. At least I don't. I mean, because well, even in the best of all worlds, you will reduce it to the smallest case, and if you don't understand the smallest case in the family, then it's a problem. That's why 3 is a magical number by now. That's the wall we hit all the time.
And maybe this is technical in the Kassenholz Scrocop paper. Do they prove it for bounded or continuous bounded?
Well, for stability, it doesn't matter because Nicolas Monod proved that if you have a lattice in a Lie group, it has the same stable bounded cohomology. I mean, below, I think, 2 times the rank. And so if you only care about the stable thing, you can do it with lattices instead of with Lie groups. And the lattices will be arithmetic, so they will act on a rational building. And that's what they use, whereas we use some so-called Stiefel complex by Foucault. So they get around the technicalities of measurability here because they work with a discrete group. And what they get from this is they get a slightly better range, but since you can bootstrap in the end anyway, I'm not sure. I mean, how much this gives you, but their approach seems to be more conceptual because they work with the building, which is the right tool to use. I mean, we had some measurability issues there, and by working in the discrete setting, they avoid them. So that's definitely a good idea what they do. Yeah.
I see. Thank you. Well, I guess Aaron is gone, so maybe I should take over. Is there any other question?
Well, I was just here to talk after because I thought that there was going to be more math talk after his talk and the recording stopped.
Sure. So let's thank the speaker then. Well, everybody is free to go if